Imagine a world where electricity could flow without resistance. Sounds impossible, right? Well, welcome to the enigma of superconductors, where the impossible becomes possible. Superconductors, they're not your average materials. These unique substances have the fascinating ability to conduct electricity without any resistance. But there's a catch. This only happens when they're cooled to certain, often extremely low temperatures. This phenomenon, known as superconductivity, is more than just a cool party trick. It's a deeply significant concept that challenges our conventional understanding of physics. We're talking about a world where energy loss could be minimized, where power could be transmitted over long distances without the usual inefficiencies. We're talking about a potential revolution in how we understand and utilize electricity. So how do these superconductors pull off such a seemingly impossible feat? Buckle up as we delve into the world of superconductivity. It's going to be a ride filled with intriguing science, baffling mysteries, and the promise of a future that could be brighter than we've ever imagined. To understand superconductors, we need to first grasp the basics of electricity and resistance. Now imagine electricity as a bunch of eager tourists trying to navigate through a bustling city. The city here represents a material, let's say copper, and the tourists are the electric current. As the tourists move around, they bump into the city's inhabitants, the atoms, causing traffic jams and slowing them down. This is what we refer to as resistance, and it's why your toaster gets hot when you're making breakfast. However, what if I told you there's a city where tourists can roam freely without bumping into anyone? Sounds like a dream, right? Well, that's essentially what a superconductor is. When certain materials are cooled down to extremely low temperatures, they become these dream cities, allowing electric current to flow through them without any resistance. The process is quite fascinating. As the material cools, the electrons, which are the particles carrying the electric charge, start to pair up. These paired electrons, known as Cooper pairs, can then move through the material without getting scattered by the atoms. It's like they've been given a VIP pass to glide smoothly through our city without any interruptions. But why is it so important that these Cooper pairs don't face resistance? Well, resistance leads to energy loss in the form of heat. If there's no resistance, then there's no energy loss. This means superconductors can carry a current indefinitely without losing any energy. Imagine how much energy we could save if all our electrical systems were superconducting. However, achieving superconductivity isn't as simple as flicking a switch. It requires chilling the material to cryogenic temperatures, often only a few degrees above absolute zero, which is colder than outer space. And not all materials can become superconductors. Only certain metals, alloys, and ceramics have this extraordinary property. With the concept of resistance out of the way, you might be wondering, what makes superconductors so special? Scene script. Superconductors aren't just about zero resistance, they have more tricks up their sleeves. Think of a superconductor as an extraordinary magician who performs mind-boggling feats that defy the laws of physics. One of those astonishing tricks is known as the Meissner effect. This is where a superconductor, in a show of sheer defiance, expels all magnetic fields from within itself. Yes, you heard that right. A superconductor simply refuses to let any magnetic field pass through it. It's like a superhero with a force field that keeps out all things magnetic. Now, this leads to a phenomenon that seems straight out of a sci-fi movie: magnetic levitation. Picture this: a superconductor and a magnet. The superconductor, with its no entry sign for magnetic fields, causes the magnet to hover above it, suspended in mid-air. It's not magic, but it sure feels like it. This magic trick has some incredible real-world applications. Take, for instance, the maglev trains. These trains, short for magnetic levitation, use the Meissner effect to levitate above the tracks. This eliminates friction, allowing these trains to reach astonishing speeds. It's like having Aladdin's magic carpet, but in the form of a train. Another application, and perhaps one you might be more familiar with, is in MRI machines. These machines use superconductors to generate the strong magnetic fields necessary for imaging the human body. Thanks to superconductors, doctors can peek inside our bodies without a single incision. But as with any good magic trick, the real magic lies not just in the trick itself, but in its implications. The zero resistance and magnetic properties of superconductors could revolutionize our world. Imagine a world with lossless power transmission, ultra-fast trains, and even more advanced medical imaging. With their zero resistance and magnetic properties, superconductors sound like a dream. But there's a catch. Like all great things in life, superconductors come with their own set of challenges. Now, wouldn't it be wonderful if we could just flip a switch and have superconductivity at our fingertips? Unfortunately, the reality is a bit more complex. The main hurdle in harnessing the power of superconductivity lies in temperature. You see, superconductors aren't exactly sunbathers. They prefer the colder climates, and by cold we mean temperatures that make the Arctic Circle seem like a beach vacation. Typically, we're talking about conditions close to absolute zero. That's minus 273.15 degrees Celsius for the metrically inclined among us, or minus 459.67 degrees Fahrenheit for those partial to the old imperial system. In practical terms, it's colder than anything naturally occurring in our known universe. Maintaining these frigid conditions outside of a lab setting is, as you might imagine, no small task. It requires intricate cooling systems and a constant supply of energy. Not exactly the most convenient setup for your average home or business, but science, as always, is on the case. Researchers around the globe are engaged in a high-stakes race to discover a room-temperature superconductor. Imagine that. The power of superconductivity, no fridge required. This is no mere fantasy. In fact, just recently, scientists have reported superconductivity at temperatures as warm as minus 23 degrees Celsius. That's a far cry from absolute zero and a significant step towards the holy grail of room temperature superconductivity. But let's be clear, we're not there yet. These high-temperature superconductors still require immense pressure to operate, and the materials used are not yet practical for widespread application. So yes, there are challenges, there are hurdles to overcome and puzzles to solve. But the promise of superconductivity, the potential to revolutionize our world, makes these challenges worth facing. Despite these challenges, the potential implications of superconductors are simply too great to ignore. Now that we've covered the basics of superconductors, let's explore what the future holds for them. In the realm of power transmission, superconductors could revolutionize the way we distribute electricity. Imagine a world where long-distance power lines don't lose energy due to resistance. That's the promise of superconductors, as they allow electrical current to flow without loss, potentially saving billions of dollars annually in energy costs. Now let's take a leap into the world of computing, quantum computing to be precise. Here, superconductors are already playing a key role. They're used to create quantum bits or qubits, the fundamental units of quantum computers. Unlike traditional bits, which can be either 0 or 1, qubits can be both at the same time, thanks to the magic of quantum mechanics. This could lead to unimaginably powerful computers, capable of solving problems that are currently out of reach. In transportation, superconductors could pave the way for frictionless, ultra-efficient travel. Picture this: trains levitating above the tracks, propelled by superconducting magnets. This isn't science fiction, it's called maglev technology, and it's already in use in some parts of the world. With further advances in superconductivity, who knows where we could go next? But let's not get ahead of ourselves. While the potential of superconductors is vast, there are still many challenges to overcome. They currently require extremely cold temperatures to work, which is impractical for many applications. However, scientists around the globe are striving to create room temperature superconductors. If they succeed, it could open the floodgates to a wave of new technologies, changing our world in ways we can scarcely imagine. The road to perfecting superconductivity may be long and arduous, but the rewards are worth the struggle. So here's to a future where superconductors are as common as silicon chips today, powering our world with efficiency and flair. Superconductors, a phenomenon that sounds straight out of a science fiction novel, are very much a part of our reality. In this journey, we've delved into the enigma that is superconductivity, uncovering the fascinating mechanics that allow these materials to carry an electric current with zero resistance. We've marveled at the magic of superconductors, where electrons dance in pairs and magnetic fields are expelled, creating levitation effects that seem to defy gravity. Yet we've also acknowledged the challenges, from the cryogenic temperatures required to the complexity of their structures. But the future of superconductors is promising, with potential applications that could transform technology from quantum computers to levitating trains. The road to fully understanding and harnessing superconductors may be long and winding, but it's a journey that's sure to be filled with exciting discoveries. As we continue to unlock the mysteries of superconductors, who knows what exciting possibilities lie ahead? Stay curious, keep learning, and until next time, cheerio.